Okay, so I wanted to talk about the elevator problem. And before that, I'm just going to talk about in the bathroom. Okay? And in the bathroom, you got your scale, right? This is an old style looking scale like at the doctor's office. Okay, there's the scale reading right there. Okay? Actually, that last one, maybe it looks more like that. Okay? And here's me, absolutely horrified looking at my weight in the scale. Okay? Oh my gosh, I didn't think I weighed that much. Anyway, let's say that this is my system. That would be me. Okay? Force diagram on me would be normal up. That's the scale pushing up on me. It's a normal force, really. And then the weight down. Now, what makes scales work, this is weight due to Earth's gravity field, is there's an assumption, there's an N1 assumption, right? Scales are used when the acceleration is 0, since A is 0. Not only is the acceleration 0, velocity is also 0, but the important part is that the velocity isn't changing. Like when you go in the bathroom, the bathroom doesn't typically start speeding up upwards or downwards, right? And it doesn't even move. So since the acceleration is 0, the forces must add to 0, and I'm giving an N1 argument there, right? So that's my N1 argument. Therefore, when I draw my vector sum diagram, adding the vectors head to tail, I see that the weight and whatever the scale reads, I'll call it F scale. Well, the normal force. Scales read normal force. So that's what I'm gonna say here. Scale, a bathroom scale reads normal force. But since in this case normal equals weight, that's why we say that a scale reads your weight. Okay? So now if we make things a little more interesting, we could have the bathroom scale and the person in an elevator, right? So let's say they're in an elevator. Now that would be the tipper. It doesn't really matter if you're moving upwards or downwards. Again, what matters is that your velocity isn't changing. So the elevator is moving in one direction, not changing speed. So now the person is inside the elevator. There's the scale, right? And there's me again, super horrified at seeing how much I weigh. And you could just play the same game. You got weight going down. This time I'll just call it normal force because it is a normal force. And since our acceleration is 0, the forces need to add to 0. That means that when I place my vectors head to tail, when I actually add them as vectors, not as numbers, but as vectors, which have direction as well as magnitude, I find that these vectors have to also have the same magnitude in this case because they're opposite direction. So normal has to equal in magnitude to my weight, whatever my weight is. And it wouldn't matter if the elevator were moving down at 3 meters per second or if it were moving up at 3 meters per second. The scale reading will be the same in both cases. By N1, the net force has to be 0, and therefore the normal and the weight are equal in magnitude. And yeah, that's a classic elevator problem. Now in the next unit, we'll talk about what happens when there's acceleration either up or down. Anyway, I hope that helps, and have a good day.